Hello differential equation students. In this video we are going to take a look at how to solve differential equations with piecewise functions. So to do that, let's take a look at one of the fundamental piecewise functions. We are going to use them very often, and that is called the unit step function. This is basically, as we denote it by ut of a. I often denote it as a ut of a because the ut is it's a kind of like a constant function, right? Not exactly, but kind of like a constant function. The only thing that matters is the a, so I kind of denote as a ut of a. But remember, a is not a variable, right? A is a constant and t is a variable. So this is okay to use it as well. So what does this function do? The function is 0 until you reach a, and then it moves up 1 unit. Then it moves up by 1 unit. Think of it this way. This is like, switching mechanism. Let's say you turn the switch on, right, of an electrical circuit at time a, right, at a time a, then there is nothing passing through on that electrical circuit. And then when you turn the switch on at time t is equal to a, then now you have like the switch is completely on, right? The circuit is completely on. The voltage or the electricity is passing through that circuit right there. So it's like that. So this is actually used to simulate. This is used in simulation that represents the action of a switch, by the way. And this comes from a function called Heaviside function. Again, this is named after the mathematician Heaviside. That's basically it's 0. The function is 0 until it's 0, and then it becomes 1 when the t happens to be greater than 0. So this is basically a shift of that function. So it's basically shifting the 0 to a is what you get this unit step function. We'll write it as this way or this way, but I'm going to mostly prefer using that way. So first things first, let's try. We are always interested. We are interested in finding the Laplace transform. So let's try to figure out how does the Laplace transform works for this, right? So what is the Laplace transform of this unit step function, which is e to the negative as over s. Let me quickly show that how that is. So if you really take a look, right, this Laplace transform of this unit function u, right, of t minus a, as you see here, that is going to be 0 to infinity, right, u of t minus a e to the negative st dt. And if you take a look at this function, this is from 0 to a, the function is 0, right? And then with e to the negative st, it doesn't matter, that's a 0 anyway, dt, plus then you have a to infinity, it is u is 1 times e to the negative st dt, right? And now this whole thing is 0. That's a history, that's gone. Now all you have is this particular side, and if you integrate that, ladies and gentlemen, you're going to have e to the negative st over negative s, and the lower limit is a and the upper limit is infinity. And if you plug it in, what you're going to have is you're going to have e to the negative as over s, right? After you plug it in, that's what you have, and that's what we have it right here. That's what you have it right here, right? And that's the derivation of the Laplace of unit step function. Now the good news with this is, using this step function, we can write down any finite linear combination of functions. So for example, here if you take a look, that's f of t, which is h of t between 0 and a, g of t between 0 and a, and h of t if t is greater than or equal to a, right? So that's just two functions. If you try to graph it, by the way, the graph is gonna look like this. Let me clean this up a bit. So if I graph this function, what I'm going to have is the following. The graph is going to look like this. The function is, let's just say this is my a. Up to this, you have this function g of t, and then that's your g of t. And afterwards, it could be a continuous function, but it does not have to be a continuous function. you may have another function, something like that. That's your h of t, right? Now, how do you write this particular function? How do you write this particular function, right? And so on is what we are going to take a look today. What if you have what if you have another one, w of t, right? What if you have another a z of t, and then what if you have so many of them, right? How do you write them? So to do that, let me just take a step back and try to look at it in terms of constants, and then we will slowly expand this into functions. All right, so let's take a look at this function, right? Very simple function, not a big deal. Suppose if I give you this function that I'm going to call the f1 of t, which has this following graph, and that is the following. So again, we are only interested in functions that are greater than or equal to 0 because of the way the Laplace is defined, right? So until it's 1, until it's 2, it is 1, right? It is 1, and then there is a hole right there, and then it is 3 from 2 to 4, and then let's just say this is -2 from 4 onwards, right? How do I represent this particular function? So this is -2, this is 0, this is 1, and this is 3, right? Now what is happening is this is 1, correct? So then what happens, I want you to think of it along this way. So it's the function is 1, then at 2 it moves up 2 units, right? From 1 it's going to 3, so it's moving up 3 units up, and then at 4 it's coming down 1, 2, 3, 4, 5 units, right? So we are going to use the step function, unit step function, to represent this this mechanism. So what I'm going to write this function as the following. The function f1 of t is equal to 1. It starts at 1, then it moves up, right? Then it's going to move up by 3 units, sorry, 2 units, right? So then what I am going to do, I am going to add 2 times that step function, right? I'm going to add 2 times the step function, u of t minus 2, because until 2, this u of t minus 2 is 0, right? And then it becomes 2, so there's already 1, and I'm adding 1 over there, right? Now what I'm going to do, I wanted to bring this down, right? At 4, I wanted to go down. How many units is going down? 1, 2, 3, 4, 5 units is going down. So what do you do? So then minus, you subtract that, minus 5 times u of t minus 4. u of t minus 4. So that's it, and that function is going to give what do we need. So let's take a look at this function again. How does it behave? See, this function is 1 throughout, right? It doesn't become 1 until it reaches 2, right? After 2, this is 1 plus 2, which is 3, right? And then after 4, this becomes what? This becomes 1 plus 2 minus 5, because this switch doesn't get activated until we reach 4, right? Until we reach 4, switch doesn't get activated. When this gets activated at 4, but then it's pulling down by 5 units, right? Then you have, that's minus 3 right there. So here is one way to represent this function right here, right? You may want to again, if you're not following, you may want to look at the video again to see how these things works, right? That's one way to represent that particular function right there. And if I write this function, by the way, if if I write this function as in algebraically, right? If I write this function in a regular way, this function is f1 of t is equal to 1 whenever t is between 0 to 2, and it is 3 whenever t is between 2 to 4, and it is -2 whenever t is greater than or equal to 4. And that is how we write this function. So here is the functional representation, and right, and here is the graphical representation of the function. Here is the representation of the function using step functions, right? And so we're going to use with that, and that's when we can use the Laplace transforms and things like that. Now, having said this, let's take a look at how this is going to work, right? But before I do that, I want to show you one other thing, and then we will take a look at that particular one right there. What I want to show here is the following. I want to see what happens when I multiply u of t with a function. How does that function is going to look like, right? Let's take a look at this one. So for example, if I take a look at, let's just say, if you take a look at, let me use a different color. If you take a look at ut of pi, right? What is the ut of pi, ladies and gentlemen? It is 0 all the way up to pi. This is, by the way, same as saying u of t minus pi, right? I like this notation. I'll tell you in a moment why that is, right? And you're going to see that. And then it's 1 when t is greater than or equal to pi, right? Now if I multiply ut of pi, because the reason that I'm writing this, by the way, the reason that I'm writing this as a pi is the only thing that matters here is the pi, right? The pi is the one that matters because it's 0 until the pi, and afterwards it's 1, right? It's almost like a constant function after that value pi, right? So if I multiply this with sine x, what is that function is going to be? That function is going to be 0 times sine x, which is 0 whenever t is between 0 to pi, and it's 1 times sine x, which is sine x, right, whenever t is greater than or equal to pi. I can just take this off. So that's the function that I have, right? That's the function that I have, and that's it. Now let me try to graph this function for you. This function, we know how does it look. This function, we know how does it look. It looks like this. So here's my pi. It's 0. It's 0 all the way here, and then 1 afterwards, right? Now how does this function is going to look? This function is going to look the following. This is 0 until it's pi. Here's my pi. It's 0 until this is pi, and then it becomes a sine x. Sine pi is 0, and this is 1, and it's going to go up and down like that, right? So here's you have a 0, and here you have a sine x function, right? Here you have a 0, and here you have a sine x function, and that's what happens when you multiply a function with the unit step function, right? This is same as, by the way, whatever you prefer, that's fine, t minus pi, but make sure to use a single notation. Don't keep on change it, then it's going to be confusing for you, right? So it's same as that function right there. u of t minus pi. So both has its own benefits, but I prefer this one. All right, now let's take a look at this function and how do we write this function right here, right? This guy right here, how do we do that? This is g of t until a, correct? So which means this is going to be, this f of t is going to be, it's going to start with g of t. Then I don't, at a, I want the g of t to vanish because I only want h of t, right? I want the g of t to vanish at a, so it's g of t until a. Then afterwards I want to be 0. I don't want this anything. I don't want the g of t anymore. So what I'm going to do, I'm going to subtract g of t after 1. How do I do that? I'm going to do that by multiplying g of t at ut of a. Now it's gone. All you have is g of t and then my 0 afterwards. But then at a, I want h back. I want h, not back. I want h. So I'm going to add h to it. So what I'm going to do, I'm going to add h to it. So if I add h to it, I'm adding h of t at a. Right? And that's what we have. And that's the function that represents f of t. The one that's in the picture or one that's over here. One that's in the picture is represent this function. So if I simplify this function, ladies and gentlemen, this whole thing is then can be simplified into g of t, think of it this way, 1 minus ut of a, right, plus h of t of ut of a. And again, if I give you 3 functions, 4 functions, 5 functions, you should be able to work with those, work with them, right? You should be able to work with them, and then you should be able to write it any way you like. Let me give you one more example, and then I will move on. So let's see how do we write this function. All right, let's take a look at this function. Let's see how do I write this function in terms of my unit step function. Again, if you take a look, until 5 it is t, and after 5 I don't want the t anymore, but I want the sine t. So what we are going to do is the following. This function is going to be rewritten as, so it's t, right, minus ut of 5 times t. That means I'm making that ut of 5 go away, and I'm adding I'm adding sine t at 5, right? I'm adding sine t at 5, I'm deleting t at 5. So that's why I like this notation, right? So the function that whatever you have written can be written this way, and you can simplify this. If you simplify this, this is t times 1 minus ut of 5 plus sine t of ut of 5. Again, there are a lot of pattern matchings you can do, right? I'll let you do that. I'll let you explore that on your own. A lot of things that you can do, you can work with them and so on. Anyways, now let's take a look at how does the Laplace transforms works with these functions. So this is called the second translation theorem, and that says the following. If L of f of t is equal to f of s and a is a positive number, then Laplace of f of t minus a ut of a, or f of Laplace of f of t minus a u of t minus a is equal to e to the minus as f of s, e to the minus as f of s. And it's basically, if you see, what you have is you're just multiplying whatever the Laplace of this without the a, whatever the Laplace of a without the a, and you're just simply multiplying e to the negative as, right? You're just simply multiplying e to the negative as with that, and that's all pretty much you are doing over here, right? So let me give you an example. But before I give you an example, let me show you a couple of things in here. Before we do the example, let's take a look at the inverse formula right away, right? Now what you have here is Laplace inverse of e to the minus as f of s, right? You remember the a. f of s is equal to f of t minus a ut of a. F of t minus a ut of a, right? Keep that in mind. And by the way, what is f of t minus a u of t minus a? That's actually the function. If you try to graph that function, right? If you try to graph the function's graph is going to look like this. F of t minus a u of t minus a is going to be 0 until a, right? And then f of t minus a after a. That's what that function is, right? And then that's what we are taking the Laplace of, right? And now if you take the Laplace, what you get is e to the negative as. F of s is what you're going to get, and that's a Laplace inverse here as well, right? Now let's take a look at a couple of these examples. All right, so let's take a look. What would be the Laplace of e to the t minus 2 u t of 2, or if you want to say Laplace of e to the t minus 2 u of t minus 2? What would that be? That would be, as per the first formula right here, that would be Laplace of this, right? But we're not going to treat this as a t minus 2, as long as you know this matches. As long as this matches, right? I would like to write this down in this way so that you can kind of see better. I'm going to write it as a Laplace of e to the t tilde u t of 2, right? Where t tilde is equal to t minus 2, as long as that comes off from here, right? Then you know I'm going to kind of a cheat in here. I'm going to treat this as if it's a e to the t, right? Because that's what matters for me for the Laplace, right? So this would be Laplace of e to the t, which is 1 over s minus 1 times e to the negative 2s. So the answer for this would be e to the negative 2s over s minus 1. Let me give you one more example so you kind of follow what I'm doing. Let me change the color. So let's take a look at this one. What would be the Laplace of ut of pi times sine of t minus pi, right? Sine of t minus pi. What would that be? That would be, since it's a pi and a pi, I'm going to rewrite it as, for my sake of simplicity, this is ut of pi times sine of, I'm going to say, t tilde, where t tilde is the t minus pi, which then this ut of pi is going to give me e to the negative pi s, and then sine of t tilde is going to give me sine, therefore it's a constant. It's going to be 1 over s squared plus 1. If I simplify that, then I am going to have the following: e to the negative pi s over s squared plus 1. As simple as that. Right? Now let me ask you this. What would be the Laplace of ut of 2 pi cosine t? I cannot do this just like that, right? The reason, because this one does not have pi inside, right? This one does not have a t minus pi. If it had a t minus pi, then I'm fine, right? If this was a t minus pi, t minus 2 pi, then it's wonderful. But I don't have this t minus 2 pi. But if you pay a close attention, that's where you have to use your critical thinking and all the trigonometric formulas that you learned. If you see that, then as a matter of fact, cosine of t minus 2 pi is actually exactly same as cosine of t. The reason, because it's t minus 2 pi is going one clockwise direction, or whatever the angle, right? If the angle is t here, then you go counterclockwise, right? That's the negative 2 pi, means you're going to get back to the same angle there, so it doesn't matter. So it's going to give you the same value. So I need to rewrite this as, I'm going to rewrite this as Laplace of u t of 2 pi. This is not mathematics, this is mathematics, right? I'm replacing t by t minus 2 pi in here. I wanted to pay close attention. Let me just in case change the color in here, because of this property, right? I can do this because of that particular property right there. Because of this property right here, I am allowed to do that, right? And now because of that, I am now allowed to do the regular. Now I can apply this formula right here. If I apply this formula right there, right, if I apply this formula right here, then I'm going to have the following, which is e to the negative 2 pi s, that is coming off of ut of 2 minus pi, times, and the cosine of t, the Laplace transform of cosine of t, which is s over s squared plus 1. And if I simplify this, this would be e to the negative 2 pi s times s over s squared plus 1, right? We can do that way. Now how do we do the Laplace inverse? Very simple, but you have to be careful in here, right? Otherwise things can trip us a lot. Now I'm gonna write it down. It's going to be much easier for you when you see me writing it, but you really have to be careful in dealing with that. So let me just I'm going to actually do the reverse process of what we did earlier, right? So what is the Laplace inverse of e to the negative pi s times 1 over s squared plus 1? Whenever you see e to the pi s, that means you're going to have u t of pi, or u t of pi, or u of t minus pi. That's okay as well, right? Now you take a look at this one. You have to be very careful. In general, the Laplace inverse of this is sine t, but we are not going to go with the sine t, but rather we are going to go with the sine of t minus pi. So that's what I'm going to write as, if you don't mind, sine t tilde, where this t tilde is the t minus pi, right? Which is going to be u of, you want to say t minus pi, times sine of t minus pi. You can write it like that, right? That is the Laplace inverse of that. By the same token, let me ask you this. What would be the Laplace inverse of e to the negative 2 pi s of s over s squared plus 9, right? Because of this right here, I'm going to have e to the negative ut of 2 pi, right? Ut of 2 pi. So this is going to be ut of 2 pi. And I'm going to simply say this is s over s squared plus 9, whose Laplace inverse is cosine 3t. So I'm going to say cosine 3t, but rather than saying 3t, I'm going to say 3t tilde. And this tilde is what? T tilde is this, this t tilde is t minus 2 pi, which would be, if I simplify that, ladies and gentlemen, I am going to have u of t minus 2 pi multiplied with cosine of 3 times t minus 2 pi. And by the way, in this case, it doesn't matter, because when you multiply, if you do the trigonometric property, this is exactly same as cosine 3t, and that's because of the trigonometric property and the 2 pi. It doesn't work every single time, but it works in this particular case, right? We can do that. Let me do one other step function of one of these things that we did earlier, right? Let's do one other step function of maybe just this one, so you can kind of see how these things work. Let's take a look at how to do the step function for the how to do the Laplace for that function. So let me copy this, and here's the function, by the way, right? So here's the function right there. Let's try to find the Laplace transform of this function. If I do that, this Laplace of f1 of t is equal to Laplace of 1 plus 2u of t minus 2 minus 5u of t minus 4, which is by the linearity property can then be written as, let me do one thing in here, let me just move this up over here, and let me move this up over here. Then this is the Laplace of 1, this is the Laplace of 1 plus 2 times the Laplace of u of t minus 2, and this is 5 times the Laplace of u of t minus 4. And if we do that, then we are going to have 1 over s plus 2 times e to the negative, no, it's negative times negative is positive, so it's going to be e to the negative 2s times Laplace of 1, which is s, minus 5 times e to the negative 4s. The whole thing is divided by s. So we can do that this particular way, and it'll work fine. All right. Now I'm going to stop this video right here. In the next video, we're going to take a look at how do we solve a differential equation that involves step functions, that involves piecewise functions in the next video.